Hi, it's Mr. Mac, and in these math skills that you need, today we're going to be looking at right angled triangles and trigonometry. And we're going to find out how similar triangles can help us find the angle of an incline and the ratio of the sides using basic trigonometry.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's Physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
Some math skills you need, and we're going to look at trigonometry. First, here's a picture of a ramp for wheelchair access to a church in Mount Annan in New South Wales. We're learning to use triangles and trigonometric ratios to find unknown angles. And by the end of this, we'll be able to apply basic trigonometry in right-angled triangles to calculate solutions to real-world problems. So let's look at some ramps. A ramp is a walkway on a gradual slope that aids people either to walk or to use a wheelchair to go up or down between two different levels. In Australia, a ramp, as shown in this picture, must be at least 1 metre wide between the rails and no steeper than 1 to 14. This ramp also is a long right-angled triangle. As we look at this picture, you can see the ramp is a sloping path that connects two different levels. If it rises at 1 to 14, then you walk 14 metres horizontally for every 1 metre you rise. So the right-angled triangle shown in the picture, the yellow right-angled triangle, is 14 across and 1 up. It doesn't actually matter how long or short the ramp is, it remains at the same angle. And this is shown by similar triangles. If I divide this yellow triangle up and shade one part of it, we'll see that two similar triangles have corresponding angles. So here's one, and here's a longer one. But they both have the same angle. So what angle does 1 to 14 form? Well, we know that a run horizontally of 14 metres gives rise of 1 metre. But if we run 28 metres across, it gives a rise of 2 metres. And if we run 42 metres across, it gives a rise of 3 metres. So the angle must be the same for all of these ramps. Let's call the angle theta. It's a common Greek letter, theta, and it's often used for any unknown angle. The slope, or tan theta, is the rise over the run. Now, tan is simply short for tangent. More of that later. Notice that the side with the rise is opposite the angle theta, and the side with the run is adjacent to the angle theta, but it's not the hypotenuse. Remember, the hypotenuse is the longest side of a right-angled triangle. So we have tan theta equals opposite over adjacent. Let's see what angle this ramp forms. We could measure the angle with a protractor. Try and line it up and measure to the nearest degree, and the angle is about 4 degrees. It's the same angle for a larger triangle with the same ratio of sides. Now, tangent or tan theta works with any right-angled triangle. If the right-angled triangle has an opposite side of 1 metre and an adjacent side of 14 metres, then the smallest angle of the triangle is 4 degrees, correct to the nearest degree. But what does tangent theta mean? Now, the word for tangent doesn't come from a triangle. It actually comes from the line that just touches a circle or a curve, as you can see in this old script from a book. It's from the Latin noun tangens, derived from the verb tangere, to touch. But it was not used by the ancient Romans who spoke Latin. No, it was first used by Danish mathematician Thomas Finck in his book Geometria Rotundi, published in 1583. And here's an extract from that book. And translated, it says, the tangent is unique to the same side. In other words, you can't have two lines coming from the one point for it to be just touching the circle. But it raises the question, tangent to what? A tangent is a line touching a circle. So let's start with that. Let's draw a circle that's 1 unit in radius and draw a radius that makes an angle of theta to the horizontal. So here it is. Now let's draw in some tangents. Firstly, a tangent to the horizontal radius. So it goes straight up, it's perpendicular. A tangent to that line that's an angle theta. And a tangent to the vertical radius. So it will go horizontally. And let's extend some lines. The horizontal line, the vertical line, and the line coming from angle theta. Now look and see what happens with some of these lines. This red segment here is exactly the same length as this red segment. And similarly, this blue segment here is exactly the length of this blue segment here. Notice the similar triangles. And please notice also that the angle theta occurs in about 3 different places, if not more. We have similar triangles, and we know that the radius equals 1 unit, as shown by these green line segments. So the tangent of theta is the length of the red side of the triangle divided by the radius. And of course, the radius is equal to 1. So here's one triangle. Here's another triangle. Both are similar triangles. Both have an opposite side, which is red. Both are right-angled. So tan of theta must equal the side opposite to theta divided by 1. So using trigonometric ratios, we can see that these can be defined in terms of a right angle. Let's draw a triangle with theta as one of the acute angles, as shown above. For the angle theta at one apex of the right triangle, the 3 fractions called trigonometric ratios can be defined by sine, cosine, and tangent. These are abbreviated as sine, pronounced sine, spelled S-I-N, cos, and tan. Sine theta equals opposite over hypotenuse. Cos theta equals adjacent over hypotenuse. Tan theta equals opposite over adjacent. So we come back to our ramp. What does the angle in the ratio 1 to 14, what does that form as an angle? Well, we use tan theta, which is opposite over adjacent, and we replace that with 1 over 14. Now, to find the angle theta, we must use our calculator. And when we do, we calculate tan theta, 1 over 14, 1 divided by 14, is 0.07142, and so on. And now we press, and there's the calculator, now we press the button Trigonometry, second, and this funny button that says tan to the -1. What it means is the inverse function of tan. In other words, we're doing the opposite process so that we find the angle given the ratio. We found the ratio, 1 to 14, calculated that, now we go second function, inverse tan. And we see that theta equals 4.0856 and so on degrees. So ramps in Australia must have an angle no greater than 4.1 degrees, correct to 1 decimal place. And we found it more accurately than just using a protractor. Well, here's an example using vectors. A car is driven 30 kilometres north, then turned and went 40 kilometres east. What's the final displacement of the car? Well, firstly, we draw a diagram. Make sure we put in north on the diagram, 30 kilometres for our first vector, and 40 kilometres for our second displacement vector. And then we find the hypotenuse using Pythagoras' theorem. So the resultant displacement vector has a magnitude of 50 kilometres, since 50 squared equals 30 squared plus 40 squared. And to find the angle theta, we use tan theta equals opposite over adjacent, which is 40 over 30. And again, using a calculator, 40 divided by 30, and then we go second function inverse tan, and we end up with 53.13 degrees by calculating. So the final displacement of the car is 50 kilometres at a bearing, that's from the north, of 053 degrees. So we've seen how to apply basic trigonometry to real-world problems. In our next video, we're going to see how we need to be thinking mathematically in order to develop our mathematical skills. I'm Mr. Mac. Thanks for watching.